What's up, Simpsonians? Still rolling here on a beautiful Sim Science Sunday. Gonna attack this next study guide now real quick about atomic theory. So this is what you guys had the project on. A lot of you didn't do the project at all, but even those of you who did, a lot of times it's hard to retain information from a project if you don't really deepen your learning. So this might be something that you guys definitely want to review pretty thoroughly. So let's start with Dalton. After Democritus, Dalton was really the first one who brought back the theory of the atoms. Okay, so he said that atoms were, that's way too thick. Restart. Tiny balls of mass. Okay, combined in whole number ratios. They were indivisible, with liberty and justice for all. So his model would have just looked like a ball. Let me see if I can do that thing that artists do to make a ball look so bad. Okay, but billiard ball, just a ball. Now he said they combine in whole number ratios, so like it would be 1 to, a 2 to 1 ratio or something like that. To form a molecule. And that's pretty accurate. We still hold true to that today. So John Dalton kind of started off the whole revival of atomic theory by saying that they were solid balls of mass, the indivisible parts. Like if you cut something, you would eventually get to a point where you couldn't cut it any further, which is kind of true with atoms, although now we know about subatomic particles. But he thought that atoms were the tiniest things, and each element had its own atoms, which they do, but he just thought they were different size balls and stuff like that. So billiard ball model, John Dalton, real simple. J.J. Thomson, okay? He came up with the plum pudding model, okay? Now I'm going to skip down to this question. We'll go back to drawing it and talking about what he said. So he did the cathode ray tube experiment, which you can look up. There's a video on the PowerPoint, pictures on the PowerPoint, stuff like that. So he passed, he had a tube of gas, and he passed electricity through it. And he saw that if he held up, so he passed electricity through this tube. Okay, and he saw that if he held up a negatively charged plate to it, it would get deflected upward. And if he held a positively charged plate, it would be attracted to that. Okay, so he determined there was charge within these things. They weren't just balls of mass with no charge, that there was charge. Okay, so he did the cathode ray tube. He saw the atoms when electricity was passing through, and electricity is just electrons moving. So he saw they were repelled by the negative because they're negatively charged and attracted to the positive. Okay, so it caused him to say that atoms weren't just solid balls of mass, but rather they had negative charges embedded within them. Okay, so he came up with the plum pudding model, and we call it that because he said it was like a bowl of plum pudding, which is a pudding with chunks of plum in it. So he said that it was this big positively charged mass with a positive charge dispersed throughout it, and within that were chunks of negative charge. So the plum pudding model, I think I also call it the chocolate chip cookie model, which is a dessert you guys will probably understand better. So he said that it was a solid ball of mass still, so he's still saying solid ball of mass, but because of his experiment, he saw there was a negative charge in there. So he said it was a positive charge with negative charge dispersed throughout it. Okay, Rutherford came up with a more advanced theory. So let's talk about his experiment. He did the gold foil experiment. So he shot alpha particles, which now we know what an alpha particle is, which is cool, right? We learned something. When you first heard about this, you didn't really know what an alpha particle was. Now you do. 2 protons, 2 neutrons, helium nucleus, positively charged alpha particles. So he was shooting these at a thin sheet of gold foil. Okay? Now, if the plum pudding model of the atom was correct, then all of these alpha particles would have punched right through because this wouldn't be strong enough to repel them. However, he saw that while most of the alpha particles went straight through, some were deflected off at random angles, even back towards the source of the radioactive decay. And so he realized they had to have been hitting something that was dense enough and positively charge to repel them. However, since most of them were going through, most of them weren't hitting anything. So he decided that the atom was mostly empty space with a densely packed, positively charged nucleus and electrons orbiting around it. Okay? That was horrible. Like a Jimmy Neutron atom. So whoop, whoop, whoop. Okay, that's a little bit better. So he said that it was mostly empty space with a densely packed positive nucleus, mostly empty space, and orbiting electrons. Okay, so this is getting on track to what we still believe today. Okay, his gold foil experiment showed him that there was something. These positive alpha particles were hitting something strong enough to repel them, but most of them were still going through. That's how he determined his model of the atom. Now, Bohr adjusted Rutherford's theory because he was using advanced physics, and he realized that they couldn't just be orbiting the nucleus, or otherwise eventually they'd crash into the nucleus and everything would explode. Okay, so he looked at hydrogen atoms. He looked at hydrogen electrons and saw how they jump between specific energy levels. Now that's why his theory was limited, because he was only looking at hydrogen. So what he postulated works well for hydrogen, but doesn't really sum up everything. And that's kind of where we're left off. We're still working on determining how electrons work exactly, and we don't really know. What we know is that we don't know. We don't know exactly where electrons are at any given point. The best we can do is kind of predict the area where they will be. Okay? So he used advanced physics and hydrogen atoms to observe these changes. It was limited because of hydrogen, and he said that they had to be in distinct energy levels. So he agreed with most of what Rutherford said, but he said that electrons were in specific energy levels. Okay, so instead of the Jimmy Neutron atom, his would look more like this: nucleus, and then specific energy levels for electrons to jump between. Okay? Okay. This next thing didn't really come over very well, so I'm going to fill out that chart, talk about it in the next video. So, atomic theory: Dalton, billiard ball; J.J. Thomson, plum pudding model, did the cathode ray tube experiment. Ernest Rutherford did the gold foil experiment, came up with the Rutherford model of the atom, which is an orbiting electron model, densely packed, positively charged nucleus. And then Niels Bohr advanced to Rutherford and said that electrons had to be in specific energy levels.